Surgical rooms necessitate special electrical considerations because of oxygen. Receptacles must adhere to stringent safety protocols. Ground fault circuit interrupters, commonly known as GFCIs, are mandatory in all patient care areas, including surgical rooms. Their primary function is to protect against electrical shock hazards. GFCIs operate by detecting even-minute imbalances in the flow of electrical current. Should an imbalance be detected, the GFCI swiftly shuts off the power supply to the circuit, thereby preventing the possibility of electrocution. Isolated ground receptacles are also crucial. These receptacles offer an extra degree of protection by isolating the grounding wire from the grounding conductors of the electrical system. This isolation effectively prevents stray electrical currents from potentially passing through medical equipment and entering a patient's body. Regarding light switches, surgical rooms typically employ explosion-proof light switches. The purpose of these specialized switches is to eliminate the risk of sparks or arcing that could potentially ignite flammable gases, such as oxygen, which are often present in surgical environments. Explosion-proof switches are characterized by their sealed enclosures. These enclosures are designed to contain any internal sparks or explosions, preventing their propagation to the external environment. Other considerations for electrical safety in surgical rooms include electrical wiring. The electrical wiring within surgical rooms must be installed and maintained meticulously to minimize the likelihood of electrical accidents. This encompasses the use of shielded cables to prevent electromagnetic interference, which could disrupt sensitive medical equipment, as well as ensuring the proper grounding of all electrical equipment to prevent stray voltages. Surgical rooms also demand stringent air quality control measures to maintain a sterile and safe environment. Proper ventilation systems are essential for removing airborne contaminants and reducing the risk of infection. High-efficiency particulate air, known as HEPA filters, are commonly used to remove microscopic particles from the air. Additionally, precise control of temperature and humidity levels is necessary to create a comfortable and safe environment for both patients and medical personnel. Emergency lighting is another critical safety feature in surgical rooms. In the event of a power outage, emergency lighting systems provide backup illumination to ensure that medical staff can continue to perform their duties without interruption. These emergency lighting systems are typically powered by batteries or a backup generator to provide a reliable source of light during power disruptions. Therefore, electrical safety in surgical rooms involves firstly, ground fault circuit interrupters, secondly, isolated ground receptacles, thirdly, explosion-proof light switches, fourthly, proper electrical wiring and grounding, fifthly, air quality control, and sixthly, emergency lighting. These measures collectively contribute to a safe environment. Now going into more detail, consider the National Electrical Code, or NEC, which provides guidelines and requirements for electrical installations, including those in healthcare facilities. Article 517 of the NEC specifically addresses healthcare facilities. Section 517.13 covers wiring methods for patient care areas, specifying requirements for grounding and bonding to minimize electrical shock hazards. Section 517.16 discusses the use of isolated power systems in critical care areas, such as operating rooms, to further reduce the risk of electrical shock. Section 517.19 outlines the requirements for receptacles and grounding in patient care areas, emphasizing the use of hospital-grade receptacles and proper grounding techniques. Section 517.20 specifies the requirements for essential electrical systems, including emergency power systems, to ensure continuity of critical services during power outages. Section 517.60 covers the requirements for electrical equipment in anesthetizing locations such as operating rooms, where flammable anesthetics may be used, mandating the use of explosion-proof equipment to prevent ignition hazards. Regarding ground fault circuit interrupters, these devices are designed to protect against electrical shock by detecting ground faults. A ground fault occurs when current leaks from a circuit to ground, often through a person's body. GFCIs work by monitoring the current balance between the hot and neutral conductors in a circuit. Under normal conditions, the current flowing through the hot conductor should be equal to the current flowing through the neutral conductor. However, if a ground fault occurs, some current will leak to ground, causing an imbalance between the hot and neutral conductors. The GFCI detects this imbalance and quickly trips the circuit, cutting off the power supply before a person can receive a dangerous electrical shock. GFCIs are required in wet locations such as bathrooms and kitchens, as well as in areas where electrical equipment is likely to come into contact with water, such as outdoor receptacles. They are also commonly used in construction sites and other hazardous environments. Moving on to isolated ground receptacles. These receptacles provide an additional layer of protection against electrical noise and interference. They are often used in sensitive electronic equipment, such as computers and medical devices. Isolated ground receptacles have a separate grounding conductor that is isolated from the building's main grounding system. This isolation prevents stray currents from flowing through the grounding conductor and interfering with the operation of the equipment. Explosion-proof equipment is designed to contain any internal explosions or sparks, preventing them from igniting flammable materials in the surrounding environment. This type of equipment is commonly used in hazardous locations such as chemical plants, refineries, and grain elevators, where flammable gases, vapors, or dust may be present. Explosion-proof enclosures are typically made of heavy-duty materials such as cast iron or steel, and are designed to withstand significant internal pressures. They also have special seals and gaskets to prevent the escape of flames or hot gases. In addition to explosion-proof enclosures, explosion-proof equipment may also include other safety features, such as intrinsically safe circuits and purged and pressurized systems. Intrinsically safe circuits are designed to limit the amount of energy available to ignite flammable materials. Purged and pressurized systems use compressed air or inert gas to create a positive pressure inside an enclosure, preventing flammable materials from entering. Proper electrical wiring and grounding are essential for ensuring the safety and reliability of electrical systems. Electrical wiring must be installed in accordance with the National Electrical Code and other applicable standards. This includes using the correct size and type of wire for the application, properly insulating and protecting the wires, and making secure connections. Grounding is the process of connecting electrical equipment to the earth, providing a path for fault currents to flow back to the source. Proper grounding helps to prevent electrical shock hazards and reduce the risk of fire. Grounding systems must be designed and installed in accordance with the National Electrical Code and other applicable standards. This includes using the correct size and type of grounding conductor, making secure connections, and properly bonding all metal parts of the electrical system. Regular inspections and maintenance are essential for ensuring the continued safety and reliability of electrical systems. Inspections should be performed by qualified electricians who are familiar with the National Electrical Code and other applicable standards. Maintenance should include checking for loose connections, damaged wiring, and other potential hazards. Any problems that are identified during inspections or maintenance should be corrected promptly. When selecting wiring for surgical rooms, several factors must be considered to ensure safety and reliability. Firstly, the wiring must be of adequate ampacity to carry the intended electrical load without overheating. Secondly, the wiring should have appropriate insulation to prevent electrical shorts and protect against environmental factors such as moisture and chemicals. Thirdly, the wiring should be installed in a manner that minimizes the risk of damage or physical stress. For surgical rooms, shielded cables are often recommended to minimize electromagnetic interference, or EMI. EMI can disrupt the operation of sensitive medical equipment, leading to inaccurate readings or malfunctions. Shielded cables have a metallic layer that surrounds the conductors, blocking electromagnetic fields and preventing them from interfering with the signals carried by the wires. Proper grounding is crucial in surgical rooms to minimize the risk of electrical shock. Grounding provides a low impedance path for fault currents to flow back to the source, tripping circuit breakers or ground fault circuit interrupters and quickly cutting off power to the affected circuit. All electrical equipment in the surgical room should be properly grounded, including receptacles, lighting fixtures, and medical devices. The grounding system should be designed and installed in accordance with the National Electrical Code and other applicable standards. In addition to electrical safety, air quality is an important consideration in surgical rooms. Surgical rooms require proper ventilation to remove airborne contaminants and maintain a sterile environment. High-efficiency particulate air, or HEPA filters, are commonly used to remove bacteria, viruses, and other particles from the air. The ventilation system should be designed to provide an adequate number of air changes per hour to maintain air quality. Temperature and humidity control are also important for patient comfort and to prevent the growth of mold and bacteria. Emergency lighting is essential in surgical rooms to ensure that medical staff can continue to perform their duties in the event of a power outage. Emergency lighting systems typically consist of battery-powered lights or generators that automatically activate when the normal power supply is interrupted. Emergency lighting should provide sufficient illumination to allow medical staff to safely perform surgical procedures and other critical tasks. The specific requirements for emergency lighting in surgical rooms are outlined in the National Electrical Code and other applicable standards. Regular testing and maintenance of emergency lighting systems are essential to ensure that they will function properly when needed. Now let's discuss specific code references. The National Fire Protection Association, or NFPA 70, the National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations in healthcare facilities, including surgical rooms. Article 517 of the NEC covers healthcare facilities and addresses specific requirements for wiring, grounding, and equipment in patient care areas. Section 517.13 outlines the general requirements for wiring methods in patient care areas, specifying that wiring must be installed in a raceway or cable assembly approved for the purpose. Section 517.16 addresses isolated power systems in critical care areas, such as operating rooms, where electrical isolation is required to minimize the risk of electrical shock. Section 517.19 provides requirements for receptacles and grounding in patient care areas, including the use of hospital-grade receptacles and the proper grounding of all exposed metal surfaces. Section 517.20 covers essential electrical systems, including emergency power systems, which are required to provide backup power to critical equipment and lighting in the event of a power outage. Section 517.60 addresses anesthetizing locations, such as operating rooms, where flammable anesthetics may be used, specifying requirements for explosion-proof equipment and other safety measures. Furthermore, NFPA 99, the Healthcare Facilities Code, provides additional guidance on electrical safety in healthcare facilities. Chapter 6 of NFPA 99 covers electrical systems and addresses topics such as essential electrical systems, electrical equipment, and electrical testing. Chapter 13 of NFPA 99 addresses anesthetizing locations and provides requirements for ventilation, gas systems, and electrical safety. It is crucial to consult both the NEC and NFPA 99 when designing and installing electrical systems in surgical rooms to ensure compliance with all applicable codes and standards. Remember that specific requirements for surgical rooms may vary depending on the local jurisdiction and the type of medical facility. It is always essential to consult with a qualified electrical engineer and the local authorities having jurisdiction to ensure that the electrical installation meets all applicable requirements. Furthermore, hospital-grade receptacles are designed to withstand the rigors of a healthcare environment and provide a more reliable electrical connection. They have stronger contacts and a more durable construction than standard receptacles. Hospital-grade receptacles are typically identified by a green dot on the face of the receptacle. Regarding explosion-proof equipment, it is designed to contain any internal sparks or explosions, preventing them from igniting flammable materials in the surrounding environment. This type of equipment is commonly used in areas where flammable gases, vapors, or dust may be present. Explosion-proof equipment must be certified by a recognized testing laboratory, such as Underwriters Laboratories, or Factory Mutual, or FM. Emergency power systems are required to provide backup power to critical equipment and lighting in the event of a power outage. These systems typically consist of generators, batteries, and automatic transfer switches. The emergency power system must be designed to provide sufficient power to operate essential equipment for a specified period of time, typically several hours. Automatic transfer switches are used to automatically switch the electrical load from the normal power source to the emergency power source in the event of a power outage. These switches must be reliable and capable of transferring the load quickly to minimize disruption to critical services. Regular testing and maintenance of emergency power systems are essential to ensure that they will function properly when needed. Testing should include verifying that the generator starts and runs properly, that the batteries are fully charged, and that the automatic transfer switch operates correctly. Another consideration is equipotential grounding. Equipotential grounding is the practice of bonding all metal surfaces in a patient care area together to create a common ground potential. This helps to minimize the risk of electrical shock by ensuring that there are no voltage differences between different metal surfaces. Equipotential grounding is typically achieved by connecting all metal surfaces to a common grounding busbar. Regular inspections of electrical systems in surgical rooms are essential to identify and correct any potential hazard. Inspection should be performed by qualified electricians who are familiar with NEC and other applicable standards. Inspection should include checking for loose connections, damaged wiring, and other potential problems. Any problems that are identified during inspection should be corrected promptly to prevent electrical accidents. Furthermore, ongoing training for medical staff on electrical safety is important to ensure that they are aware of the potential hazards and how to prevent them. Training should include topics such as how to recognize and report electrical hazards, how to use electrical equipment safely, and what to do in the event of an electrical accident. In addition to the above considerations, it is important to follow the manufacturer's instructions for all electrical equipment used in surgical rooms. This includes using the correct power cords, plugs, and adapters, and avoiding overloading circuits. Overloading circuits can cause the wiring to overheat and potentially lead to a fire. Electrical equipment should be regularly inspected and maintained to ensure that it is in good working order. Any damaged or malfunctioning equipment should be removed from service and repaired or replaced. The use of extension cords should be minimized in surgical rooms. Extension cords can be a tripping hazard and can also overload circuits. If extension cords are necessary, they should be heavy-duty and properly grounded. They should also be inspected regularly for damage. Water and other liquids should be kept away from electrical equipment. Water can conduct electricity and create a shock hazard. If electrical equipment gets wet, it should be disconnected from the power supply and allowed to dry completely before being used again. Moreover, static electricity can be a hazard in surgical rooms, particularly when flammable anesthetics are used. Static electricity can create sparks that could ignite the anesthetics. To minimize the risk of static electricity, the humidity in the surgical room should be maintained at a certain level. Also, medical staff should wear cotton clothing and avoid wearing synthetic materials that can generate static electricity. Additionally, grounding straps can be used to discharge static electricity from equipment and personnel. In summary, electrical safety in surgical rooms is a complex and multifaceted issue. It requires careful planning, design, installation, and maintenance. By following the NEC, NFPA 99 and other applicable standards, and by implementing the safety measures, healthcare facilities can minimize the risk of electrical accidents and provide a safe environment for patients and medical staff. This includes ground-fault circuit interrupters, isolated ground receptacles, explosion-proof light switches, proper electrical wiring and grounding, air quality control, emergency lighting, adherence to code requirements, hospital-grade receptacles, explosion-proof equipment certification, emergency power systems and testing, equipotential grounding, regular inspections and training, following manufacturer's instructions, minimizing extension cord use, keeping liquids away from electrical equipment, and controlling static electricity.